Today in Chapter 9, we're going to go a step further in stoichiometry by looking at mass calculations in Section 9.3. All right, so one of the things that I want to have you write down and remember is our pathway again. So remember that if we are at grams and we want to go to moles, we go straight from grams to moles, and we use the molecular mass or the molar mass of the compound. If we want to go to moles, then we can go to molecules, and that was Avogadro's number. We talked about this being the pathway here. Avogadro. And here we're going to use molar mass. Okay, another thing that we talked about in the last video was a mole-to-mole ratio, that we compare moles to moles. So while this is the pathway that we can travel if we want to go molecules, moles, and grams back and forth, this is what we would use. In stoichiometry, look at mole-to-mole ratios because we need to compare the relative moles of reactants and products, or to be able to predict the amount of products based on the amount of reactants, and we can't compare their masses, so we have to go to moles. So we do a mole-to-mole ratio. And then I can take that and go to grams. So in the lecture for the first and second sections of Chapter 9, all you had to do was a mole-to-mole ratio. Today we're going to introduce mass calculations. So we're going to be at grams, and we want to get our answer in grams. And in order to do that, we have to go from grams to moles, do our mole-to-mole ratio, and then go from moles to grams. Now, the cool thing about this is that if my problem says I have moles and I want to find out at moles of reactants and I want to go to grams of product, I still go a mole-to-mole ratio, but then I can go ahead and turn moles of product into grams. So I can start by giving grams and go all the way to grams as a product. The best way to do these is to look at a couple of examples. So let's start with some basic steps for calculating the mass of the reactants and products. So first of all, you always start with a balanced equation for the reaction. Then you're going to convert masses of reactants or products to moles, use the equation, the balanced equation, to give you a mole-to-mole ratio setup, and then use the number of moles from the ratio to calculate the number of moles of the desired reactant or product. The 4 basic steps of mass calculation. Then you're going to convert from moles back to masses. So this is really similar to what we've done in the last 2 sections. The only difference is we have masses involved, and those masses, before we can do anything with them, must be turned to moles first. Stoichiometry, by definition, is the process of using a balanced chemical equation to determine the relative masses of reactants and products involved in a reaction. Now, stoichiometry is a big word, a confusing word in chemistry, I guess. It doesn't really seem to make a whole lot of sense, but this is something that it's not a foreign concept. We've been in the lab before and done labs, and we've talked about how that kind of relates back to cooking, because cooking is a process in a lab, in your kitchen lab, and we talk about if I have enough of this one or not enough of this one in order to make the product that's desired, or how much of this reactant and that reactant, how many eggs do I need, how much water do I need, how many cake mixes do I need in order to make that cake. This is something you do on a practical level, but in chemistry class, because it's a little bit different and it's scientific, we're going to look at it a little more critically and a little bit more specifically when we look at the amounts. Not just a couple of these, a couple of those. We have specific amounts that we're going to deal with. So we're going to use stoichiometry, or talk about stoichiometry, because that's the calculations that you're going to be doing, or those involving stoichiometry. So let's start with an example. It says for the following unbalanced equation, and there's unbalanced. You've got to make sure that you're balancing it. So we have to make sure that this gets balanced first. How many grams of chromium 3 oxide can be produced from 15 grams of solid chromium and excess oxygen gas? Now, for our process, I'm going to rewrite this problem down here so that we can see it, and I can show you how I want to see you set up the problem every time you do it. And it's not anything much different at all from yesterday's assignment. So let's start off by balancing the equation. So we probably need a 3 here, and we probably need a 2 here to balance our oxygen, and a 4 here. So now we're balanced, and that step may take you a little bit longer depending, so don't get frustrated with it. Always start with a balanced equation. Now write down the information from the problem, just like we did before. How many grams of chromium-3 oxide? Here's my chromium-3 oxide. They want to know how many grams. Notice I put a G there for grams to remind me that I'm going back to mass. I'm not going to stop at moles like I did before. Can be produced from 15 grams of solid chromium and excess oxygen gas. Let's write down what we need to help us remember here. So if we come up here, remember that it's grams to moles. If we have grams, a mole to mole ratio, and then back to grams. So let's look and see what we've been given. We've been given grams, and we want to go to grams, and we're given excess oxygen. So this doesn't come into play for us today. So we're at grams, we want to go to grams, we have to do a mole to mole ratio. So we're going to take grams to moles and do our mole to mole ratio, and then change moles back to grams again. So let's start with taking 15 grams of chromium, and the molar mass of chromium is 52 grams per mole. So we're going to put 1 mole on top and 52 grams on the bottom. We do the calculation, we take 15 times 1 divided by 52, and we get 0.288 moles of chromium. So we've gone from grams to moles. Our next step then is to do a mole to mole ratio. Remember from yesterday's video that we're going to take the things that we're looking at, the compounds or the elements that we're looking at. So chromium, and we're going to compare that and do the mole to mole ratio with the chromium-3 oxide. Remember that our top number, just out of habit so that we're doing it the same way every time, comes from the balanced reaction. So the balanced reaction says it should be 4 chromium needed for every 2 chromium-3 oxide. Number on bottom is going to be from the problem. We know that we have 0.288 moles of chromium. We want to know how many moles of chromium-3 oxide. We're going to cross multiply. So that's going to be 4x equals 2 times 0.288. Just to save us some time, let's go ahead and divide that side by 4 and that side by 4 so we get x by itself. So 2 times 0.288 divided by 4 is going to be 0.144 moles of Cr2O3. And be careful with your labeling. Take time to put moles, what compound it is, or what element it is. It makes so much difference, especially when I go to give you partial credit, because if I can follow your scheme and see maybe you've just made a simple math error, you're not going to get near as many points taken off as if I can't follow your work. So this is how I want it set up. Now sometimes they would say, how many moles does that produce? So there, that would be your answer. However, in this case, we don't want moles of chromium-3 oxide, we want grams of chromium-3 oxide. So what you have to do is you have to figure out how much the chromium-3 oxide's molar mass is. This is going to be 104 for the chromium. We have oxygen at 3 times 16, which is going to be 48. So the mass of our chromium-3 oxide is 152 grams per mole. We're going to use that down here, and we are going to change that to moles, so times 152. So 21.89 grams of Cr2O3. There is your final answer. We have the number, we have the units, which is grams, and we have the compound or the substance, which is the chromium-3 oxide. So to go back and look at the problem again, how many grams of chromium-3 oxide can be produced from 15 grams of solid chromium and excess oxygen gas? The answer is 21.89 grams of chromium-3 oxide. Look at the next exercise. Tin 2 fluoride is added to some dental products to help prevent cavities. Tin 2 fluoride is made according to the following equation. And if you notice, this is a balanced equation, so we don't have to worry about doing the balancing. How many grams of tin 2 fluoride, take my pen again, how many grams of tin 2 fluoride, so I'm going to put it on top this time just because of the way this is written, how many grams can be made from 55 grams of hydrogen fluoride which is hydrofluoric acid, not really hydrogen fluoride, hydrofluoric acid, if there's plenty of tin available to react. So this is our excess. We don't have to worry about how much tin, we have enough of it. So again, we're going to look at our problem, and we notice that we have grams, and we want to go to grams. So we're going to do grams to moles. We're going to do a mole-to-mole ratio, and then we're going to change that answer back to grams again. So 55 grams of hydrofluoric acid. So the mass of hydrofluoric acid, chlorine, is 19. So it's about 20.01 grams per mole. I'm going to take my 55 grams, and I'm going to change that to moles by taking 20.01 grams. So 55 divided by 20.01 is going to be 2.75 moles of hydrofluoric acid. We're going to then, we've done grams to moles, we're going to then concentrate on our mole-to-mole ratio. So we have hydrofluoric acid, and we have the tin-2 fluoride. We go from the balanced reaction for the first one. So the balanced reaction says for every 2 hydrofluorics, I should be able to produce 1 tin-2 fluoride. The bottom number, remember, is from the problem. The problem says I have 2.75 moles of hydrofluoric acid. How many moles of tin-2 fluoride do I need? Or will I produce, I'm sorry. 2x, we're going to cross multiply, is 1 times 2.75. Divide both sides by 2, so x equals 2.75 divided by 2. So x equals 1.37 moles of SNF. At this point is where I start to see students get lazy, because you'll get 1.37 and not put a unit and not put a substance with it, and when you go back to look for that information, you're not really sure what it was that you found or what the units are on it. So make sure that you take the time to do this. When we get to limiting reactants, it's going to be very important that you remember that. So we're back to this problem. We did a mole-to-mole ratio. If we start off with 55 grams of hydrofluoric acid, which was 2.75 moles, I should end up with 1.37 moles of tin-2 fluoride. Now the problem doesn't say to stop with that. The problem says I want to know how many grams that will be. So I'm going to change that to grams. So let's go up here and do the mass of tin-2 fluoride. That's 118.71. We have fluorine, which is 19 times 2. So if we take the 19 times 2, add that to 118.71, we have a total of 156.71 grams per mole. So I'm going to come down here, I'm going to change color so it'll show up on the black as well. I think they're red. Well, we'll try it. We're going to take that, we're going to multiply it by 156.71 grams over 1 mole. Cancel your moles. So times 1.37. So we have 214.69 grams of SNF2. So if you're doing the problem, this is your final answer. You're going to put a box around that. And if you go up here, you notice that'll round up to 215. So if we were doing this as a multiple choice question like we have on our test, our answer would be 215, or B. This video is running a little long. It's almost 15 minutes long, which is the limit for the screencast. So we're going to go ahead and wrap this one up now, and I'm going to do an additional exercises video for section 9.3. In order to be able to get help in class, you need to have notes over this particular section. And if you are having additional problems, I'll help you with it. If you're confused at this point, you need to go ahead and watch the other mass calculation video to give you a little bit more practice with how to do these types of problems.